Started, I'll give you an introduction and can get going. All right, it's a delight to welcome Jens Koch here for our seminar this week. He is at Northwestern University and he's been there for about 12 years, I believe, studying superconducting qubits. And I believe this is after an interesting journey to get here, because your PhD was in single molecules as transistors, if I remember. And then you met Steve Girvin at Yale and jumped into a postdoc in something completely different, superconducting quantum computation. Wrote one of the seminal papers in transmon, that introduced the transmon to the world, which is now the primary component of most experimental superconducting quantum computers. And now you've spent years developing software and all sorts of fun things. And I believe recently you're also a member of 2 separate National Quantum Information Science Research Centers of the 5 that were funded by the NSF, which is a huge success. So we welcome your expertise and are very interested to hear what you have to say.
Thank you very much. I will go forward and share my screen as long as I manage. And I'll share the one down here. And I'll have to start my slideshow. I'll probably have to switch around which screen is what. That's always the case. Display settings, swap. That looks better. And can you just confirm that this is now looking good for you?
Looks great.
Excellent. So thank you, first of all, for the invitation. Thank you also for the kind introduction. It's I wish I could be there in person. This week was particularly difficult because we have a faculty search going on and I'm playing chair for that. And so I can't easily leave in the middle of that. But great to be here sort of remotely and in Zoom mode. I'd like to tell you a little bit about some recent work, some work that is by now probably a year old. And some of it will have to do with transmon, and some of it will have to do with circuits that we've come to love maybe even more than the transmon. Since somebody just asked about, where am I located, where's Northwestern, I did put the next slide back into the deck. So this is where we are. Chicago is a little bit south of us, a 20-minute metro ride away. And Evanston is where Northwestern's main campus is located. It's right at the waterfront. I can tell you, though, that since it's winter, it doesn't quite look as nice and friendly, but hopefully in May, it will start being back to friendly and green. The 2 centers that you mentioned are, I think you said NSF, that they're DOE centers, and I'm showing one of them to you because I had to turn deputy director for that one. So this is the SQMS center, and just to give you sort of a feel for how large these centers are, there are 26 institutions in them. Here at Northwestern, I'm overseeing 16 PIs, and it's a lot of fun. And so some of the research that I'll be talking about is funded by the DOE through SQMS, and then on the other side, it's the C2QA Center. SQMS is hosted by Fermilab as the national lab, and C2QA is Brookhaven National Lab. And since oftentimes, when talks somehow run out of time, the thing that goes missing is sort of showing you the people who do the actual work, I thought I would start with introducing you to my group. This is currently us. And that there are all kinds of stereotypes about how incapable theorists are in real life. And so this photo took a long while to take, and actually, there's a GIF that one of my students made that documents how difficult it was. This is him trying to run from the camera back to us and getting in place, and clearly that failed. All right, now some of the research that we currently do is centered on error protected qubits, and I will explain a bit more what I mean by that. And some of the examples that go under that name are, 0 pi qubit. We've worked a bit on the current mirror qubit, and then heavy fluxonium is maybe what we're focusing on most these days. I will not talk that much about autonomous error correction, error mitigation. I just, I have to make some choices. Time is finite. We do work on quantum optimal control as well. And I will talk a little bit about scqubits, which is this Python package that just, personally, I'm very proud of, because I actually contributed a whole bunch of code to it, and it's been a lot of fun. So I'll talk some about that in the second part. That is indeed the plan. Now, I actually don't know how much all of you know about superconducting qubits. I know that some in the audience do know about them, and so I don't know. Some of you are on my Zoom screen. If you want to give me a hand sign that you know about superconducting qubits and that I should go relatively fast, then I'll do that. And if I don't see any hands, then I'll go at a more moderate pace and give some introduction.
I think it's about 50-50 of students
50,
and postdocs who know it and people who are less familiar. So that's in between.
Great. That means that I can't do it right. But that's how it goes. So then I'll try and do a compromise. So I had very introductory slides in the beginning, and I think I can more or less skip over that, just mentioning that despite the fact that I have worked on superconducting qubits for a while, that is by no means the only hardware platform for quantum computing. They're very promising alternatives that I won't speak about, but that doesn't mean that I necessarily think that superconducting qubits are the best or that they will win some race. It's just what I've been working on. Currently, they seem to be popular, but things can change. So 50% of you know what the superconducting qubits are. 50% of you may want a little bit of introduction and guidance. So that is what I'll do next. These circuits are very simple circuits in the sense that there are no transistors, there are no fancy circuit elements other than 3 that we currently use, and those are capacitors, inductors, and Josephson junctions. So the simplest circuit that you've all seen before is an LC circuit. The only thing that is different here is that you use a superconductor or superconductors to make up this capacitor and this inductor. And with that, you will find that the system actually behaves quantum mechanically. So the flux through the loop, through the inductor, and the charge on the capacitor, they actually become operators, and your classical LC oscillator turns into a quantum LC oscillator with an equidistant energy spectrum. Equidistant energy spectra are not the best to work with if you want to create a qubit. It has to do with the fact that if you just use a coherent tone, a sinusoidal tone, then you will not be able to selectively steer the system and remain in just the lowest 2 states. You will create a coherent state that involves all kinds of Fock states. And so we want a little bit of nonlinearity that breaks this equidistant energy splitting. And that's precisely what Josephson junctions do for us. And so instead of a parabola, this Josephson junction, what does it do for us? It creates a cosine potential instead of this parabolic potential. And I could say a few things about the nature of Josephson junctions and how they work, how Cooper pairs tunnel across from one superconductor to the other. And I think I'm going to skip over some of these details to just focus on the quantum information part. But if you have questions, I'll be happy to answer those and come back to them. In fact, if you have questions as we go along, please feel free to interrupt me, and I'll be happy to entertain questions as we progress. So we have a cosine potential. How does that help? Well, a cosine is different from a parabola, and accordingly, the energy levels that you find inside that potential are not equidistant anymore. They sort of diminish in energy spacing as you go further up. And an approximation that you will see very frequently is you can write this Hamiltonian, rewrite this Hamiltonian as a I have a feeling that you can't see my cursor. Let me see whether I can make you see my cursor. That should be better. Here's your harmonic oscillator. That is what we didn't like as much. We wanted some anomicity. And so the second term here is precisely what provides that, or what describes that anomicity. Every step that you go up, the splitting actually decreases by an amount that is called alpha here. Alpha turns out to be the charging energy associated with this capacitor, in fact. What does a device like that, what do they look like? These days, the circuit is called a transmon. It's in fact the same circuit as a Cooper box. It's just a different parameter regime. And it's a very, very simple circuit, right? You have a capacitor. So here's one capacitor plate. Here's the other capacitor plate. And then the thing in the middle that connects them is a thin wire, and then at the center, it actually, at this resolution, to me, looks like it's just broken, but that's where the Josephson junction is. That's where Cooper pairs can tunnel from one capacitor plate to the other. That makes up our transmon qubit. And if you're interested in sort of materials and how is this actually fabricated, then there's a little bit more information here on, the substrate is usually sapphire, sometimes silicon. And then the metals that you see are superconducting metals such as niobium, aluminum, and more recently, tantalum seems to be a nice choice that has cleaner surfaces and produces devices that perform better. Now, I'll talk a bit more about the transmon but sort of with a little bit of a critical view. They work quite well, but I think there's certainly room for improvements. Transmons were not made for some of the purposes, for some of the functions that they fulfill these days. And there's actually some funding from the ARO specifically to explore circuits other than the transmon. So in this past round of funding calls, that there was a lot of emphasis on for instance, fluxonium, and I think some of you actually know fluxonium quite well, and I do as well. So what's fluxonium? It's sort of a transmon where you introduce yet another element. So you put an inductance here in parallel with what looks like a transmon. And we could talk a little bit about the nature of that inductor and the fact that it's actually not a solenoid or not a spiral, but actually is made up out of Josephson junctions itself. But as far as the modeling is concerned, this is a pretty good model. So you get this interesting looking potential. And if you thread a magnetic flux through that loop, this potential actually changes. And depending on the particular configuration, you can have wave functions that live in one of the individual minima that you see move right now. They can spread out over multiple. There's symmetry points where you basically have a local double well that is symmetric. You get symmetric and anti-symmetric superpositions, and so on. And then over time, we got interested in circuits that are slightly more complicated even. There's a circuit that initially was proposed by Brooks, Kitaev, and Preskel. It's called the 0 pi qubit for reasons that I will talk about a little bit. And you can tell, well, it has a couple more elements, but not that many more. And the purpose or the reason why the circuit might be of interest is that it has some intrinsic protection from the noise that we know affects our superconducting qubits and limits coherence times. It has this protection in a certain parameter regime. And so just so that you're not surprised or disappointed in the end, this parameter regime is tough to reach experimentally. So there's some beautiful theory work that underlines that this protection in principle is there. And we will see that the most recent experiment, maybe not the most recent, but in fact, all the experiments that have been achieved in implementing the circuit do not quite reach the desired parameter regime yet. I think there's an animation here. So what you see is actually the potential energy, which for this circuit, after a simplification, is a two-dimensional energy landscape. And so if you kind of zoom out a little bit and let this rotate, this is what it looks like. So it's a potential energy that is periodic in the direction into the screen currently, and then has something that actually looks like a fluxonium in the perpendicular direction. And interestingly, we've played with this circuit, we've played with other circuits. As they get more complicated, the potential energy becomes multidimensional. So you recognize on the left fluxonium, then 0 pi. In fact, 0 pi has 3 variables. And so the middle one is already a simplification. And then in principle, whenever you add another node or another element in the right way to your circuit, this potential energy acquires one more spatial, if you will, dimension. And we have looked at circuits which here's one. It's called the current mirrors qubit, which was also introduced by Kitaev. And that one turned out to be a good circuit if you include 23 variables, x1 through x23. And that's something that my former graduate student, Danny Weiss, who's now at Yale, worked on. And that circuit, again, has some promise to provide you with protection from noise. But you can imagine that it's not easy to build. Northrop Grumman actually tried and again didn't quite reach the parameter regime in which full protection could be achieved. For those of you who are in the 50% of you're knowledgeable, but maybe you don't work with superconducting qubits all the time, I have 2 or 3 slides that just give you a flavor of how do you actually control and read out these qubits. Right now, I'm just showing you an isolated circuit. How do you manipulate its quantum state? How do you learn something about its quantum state? And you can do that by coupling your qubit to either a 3D cavity, like the fancy Fermilab cavity that is shown here on the left. Equally, you can decide to do everything in 2D on the surface of a substrate, and then this transmon just gets embedded in a coplanar waveguide resonator. Here's the 3D version. So you take this transmon circuit, which this one has a slightly different aspect ratio. Here are the 2 capacitor pads. Here's the Josephson junction in the middle. And so you take that and you basically stick it into the 3D cavity where it interacts with the electromagnetic field inside. It's like a big antenna, right? It's a big dipole, and the electric field couples to it. And as I said, the 2D version works just as well. This is yet another way of shaping your qubit, and this line here that meanders around just to save space on the chip, that is one of the resonators that couples to this qubit. And if you want to know a little bit more about how do we model this, how do you actually predict something, how do you do a calculation of what's going on, the simplest model that is a really good starting point to understand the physics is the Jaynes-Cummings model. So you have a 2-level system, that's our qubit. You have a harmonic oscillator. That's the bosonic mode inside your cavity, and the 2 couple to each other. Once you then shine light, in this case, microwave radiation, either onto your bosonic mode, the cavity, or onto your two-level system, you can manipulate the state of the qubit like such. So you shine light perhaps on the cavity, and that light ultimately makes it to your qubit, and you can induce Rabi oscillations. And if you stop at the right time, you've performed a gate. And similarly, which is actually something that the Fermilab team is pursuing, you can think about using this qubit just as an auxiliary building block that allows you to manipulate the quantum state inside the cavity. So in that case, this thing is actually not really your qubit. It's just a nonlinear element that allows you to store and manipulate quantum information in the cavity. So what you see here is the Wigner function that, under some interesting pulse, apparently is changing from something that looks a little bit like first a coherent state, then a Fock state, and then a cat state of some kind. Okay. And then on the sort of theoretical side, how do you model this? In many cases, working with a Lindblad master equation is enough. Probably quite a few of you are familiar, but just to say this in words, the object of interest then is the density matrix. You have terms that describe the unitary evolution due to the system Hamiltonian and time-dependent drives that you feed in. And then there are terms that describe the loss of photons, the T1 of the qubit, so spontaneous relaxation and pure dephasing. And since this equation or this formula already looked long enough, I pretended that we're at 0 temperature, so there are no thermal excitation. Okay. I said that transmons are nice. In fact, yes, they're currently the most used superconducting qubit, probably by quite a bit. But they're not perfect, and in some ways they are as bad as it can get. Let me try and explain what I mean by that. So on the side of pros, it's a simple circuit, and for reasons that I understand, I think experimentalists like simplicity. If it's simpler to fabricate, if there are fewer moving pieces, quote unquote, then that makes life simpler, and there are perhaps fewer ways in which this can fail. However, you saw that the energy levels of the circuit, they form sort of localized states in a cosine well. And as long as you deep inside the cosine well, it's not so different from a harmonic oscillator. So the transmon really is a weakly anharmonic oscillator. And as such, it is not at all protected from spontaneous relaxation. As soon as your environment couples to that circuit, either capacitively through the charge operator, or, well, in some cases, inductive coupling can be a thing too, maybe not for fixed frequency transmon, but you can easily relax from the first excited state to the ground state. If you do Fermi's golden rule calculation, then those matrix elements are of order 1. There's no protection whatsoever. And so will transmons be good enough to reach the threshold that is needed for quantum error correction? Perhaps. There's still interesting work based on material science in part. I mentioned tantalum earlier, that has led to quite impressive increases in T1 times. But it is, I think, worth thinking about the question, can we do better without fancy material science? Are there other ways in which perhaps we can build circuits, slightly different circuits, where some protection from noise is actually built in? So I'll talk a little bit about that, and I'll make sure that I watch my time here. So qubits are affected by noise. You know that, I'm sure. Superconducting qubits in particular are sensitive to a whole laundry list of noises, and 1/f charge noise and flux noise are probably among the worst for dephasing. and then dielectric loss is often the culprit for limiting our T1 times. And so, right, the way this goes is whenever noise is present and couples to the qubit, there's decoherence, and as far as a computation is concerned, decoherence means there's an error. And so if your future quantum computer runs an operating system like Windows, whenever you get an error, you would get a bad blue screen error message. And so clearly there's a necessity for us to mitigate errors, and especially if we're not in a position yet where we can do full error correction, we have to think carefully about how to mitigate this issue. The two kinds of errors that we like to distinguish are, I'll start with depolarization. You've seen that, I've talked about it. In the simplest case, it's just the spontaneous relaxation from the excited to the ground state. And that rate can be calculated in most cases quite simply by using Fermi's golden rule. So you have a noise spectral density that describes your environment in a simple way. There's an operator by which that noise couples to your qubit. And then that operator, in fact, through its transition matrix element between 0 and 1, mod square, tells you about the rate of this spontaneous process that for your quantum computation corresponds to an error. The other problem that superconducting qubits face is pure dephasing. And the simple-minded picture of what's going on there could be you have your qubit, it has a certain energy splitting omega q, and due to the presence and influence of noise in the environment, the splitting, oh, I thought I hadn't, I'm just going the wrong direction. That splitting, there we go. That splitting can change as a function of time. And if you think about what that means, then it's relatively easy to see that, when you consider a superposition state, which here now is represented as a density matrix, then there's a relative phase between your 0 and your 1 state. As you let time progress, the dynamical phase factor is governed by this omega q. But if that omega q varies randomly in time, then you basically scramble that phase, if you will, and your density matrix turns from something that looks like a coherent superposition into this state, which is a mixed state in which that phase information has been lost. And the timescale over which that happens is it's called T phi here because I'm talking about pure dephasing. Again, what matters is you have one factor that has to do with the noise. That's in fact the noise now evaluated at 0 frequency, as long as your noise is not singular there. And then the other factor is actually simple to understand. So suppose that the parameter that is fluctuating is called lambda. This could be flux, this could be an offset charge, and that is what sort of is the time-dependent quantity that randomly varies. And this derivative just measures the linear sensitivity of your qubit frequency to that particular noise. And so we'll see that these two expressions actually give us some hints as to what should we be looking for if we want intrinsic protection from noise in these circuits. Overall, there are a number of strategies to deal with errors. This goes sort of from the strategy that we follow, not myself, but smarter people follow doing material science, inventing new fabrication processes, and also doing microwave engineering to some degree, right? You try to actually reduce the noise. In both of the expressions that I showed just a moment ago, you have S of omega. If you make the noise smaller in amplitude, your dephasing and depolarization times are going to grow. So that would be good. That tends to be difficult, and it's something that I generally can't help with. But what I can help with, I hope, or at least as part of collaborations in the past that there has been some success, is we can try to, instead of lowering the volume of the noise, we're going to try and give our qubit earplugs, if you will. So we're going to make the qubit less sensitive to the noises that we recognize as dominant. And that means finding ways to reduce transition matrix elements in magnitude and to reduce the linear sensitivity of our qubit frequency with respect to fluctuating quantities. And then, yeah, I sort of stuffed the 2.5 in between here. There's more work that is sort of dynamical in nature, but it's not quite full-blown quantum error correction yet, where you can sort of spin your qubit around, and it turns out that if you spin it in the right way, you can actually gain a little bit in terms of the effective depolarization and dephasing times that you experience. Well, yeah, at the very end, and hopefully one day, we will be able to realize quantum error correction, where you actually monitor for errors in a smart way. You have a detection that doesn't destroy your quantum state and only extracts the information, what kind of error occurred, so that you can then correct for that error. But we're not quite there yet, although in some places I think we're getting close. So intrinsic noise protection, what would that look like? We saw that depolarization, the rate for that has this expression, and one very simple idea to reduce that rate is to say, all right, there's a transition matrix element. Imagine that your qubit, in this example, it has two variables. They're sort of written as spatial variables here, and I'm coloring the region in this plane where my ground state wave function psi naught and my first excited state psi 1, where they have significant amplitude, right? So they're pretty much zero everywhere outside, and then psi 1 is concentrated here, psi 0 is concentrated there, and since they're nearly disjoint, they're localized in different regions, any expression for a transition matrix element like that is going to be exponentially suppressed. So that's nice. You just have to imagine writing this out as an integral over x1, x2. There's going to be one wave function psi naught inside, one wave function psi 1, and some simple local operator in between the two of them. And since they localize in separate regions, that matrix element, all such matrix elements will be very much suppressed. So that's good. What about dephasing? So for dephasing, this becomes a matter of how flat are your energy levels, or how flat is your qubit splitting, if you will, with respect to important fluctuating parameters. And this is again a very simple-minded example where I'm plotting this qubit frequency, and this is my supposed fluctuating parameter, and you can tell that I'm sort of saying that, okay, the variation here is supposed to be very small. And there are examples for both of these things at work. So for transmons, that's in fact in part why transmons are successful, right? The first superconducting qubits were Cooper pair boxes, actually the same circuit, but in a different parameter regime, and they suffered dramatically from dephasing due to charge noise. And what the transmon achieved is it has energy levels that basically are independent of this offset charge. They really don't care about whether there's a fluctuating charge in the environment or not. And that increased their dephasing times from the original 1 nanosecond that was typical for a Cooper pair box in the beginning to, well, things of the order of tens to hundreds of microseconds now. This disjoint support business is also not new. It was what actually made flux qubits, I have long T1s and actually hold the record in superconducting qubit T1s for a while. And the challenge in this intrinsic noise protection overall is to, well, somehow find a way to combine both of these mechanisms in one circuit, make them work at the same time. Okay, in the interest of time, I'm not sure. I'll skip over the double Cooper pair tunneling for now. We can come back to it in the question period if you want. And I'll show you the example of the 0 pi qubit and tell you a little bit about how and why sort of both of these effects, both of these mechanisms work out in 0 pi, at least as long as you're in the right parameter regime. So the circuit looks like this: 2 Josephson junctions, 2 inductances, 2 capacitances, and we could spend a lot of time, well, not a lot of time, but we could spend some time talking about how to quantize the circuit, how to analyze it. I'm just flashing the Hamiltonian here, and we'll immediately return to something more intuitive in a second. But the message, I think, should be that if you haven't done this yourself, then there is a systematic procedure for going from a drawn circuit like this one to a quantum Hamiltonian, which looks a little bit more complicated than the one of the transmon here, but it has a simple enough structure. There's some term here that tells us about a potential energy here, kinetic energy terms, and I'll visualize this potential for you on the next slide. Here it is, at least after a little bit of simplification, so you can take a step and under certain conditions, it reduces to something two-dimensional. This is nice. This is the thing that I showed you as this rotating potential energy earlier. And so along one direction, namely this direction, it looks quite a bit like a Fluxonian potential. There's a parabolic background and a cosine modulation on top. And then if you go in the perpendicular direction, it actually looks like a transmon. So in this direction, it's periodic. And altogether, this combination, maybe not magically, but remarkably, lead to something that can have protection from both depolarization and dephasing. How? Well, you have to arrange for parameters to have certain, not certain values, but we need to be in a particular parameter regime where the fictitious particle, if that's how you want to think about it, the fictitious particle that lives in this potential must have a mass that is heavy in the vertical direction and it's light in this direction, so that wave functions like to spread out horizontally, but it's difficult to tunnel vertically. And the mass of the fictitious particle actually just corresponds to capacitances in the circuit. So it's relatively simple to see that capacitors are what boils down to your kinetic energy terms here. And if you take that at face value, you can actually compute those wave functions. And you see that indeed the ground state wave function is spread out along theta equals 0. And then the first excited state wave function is spread out along theta equals pi. So there's 0 and pi, which indeed explains why this is called the 0 pi qubit. So this visualizes nicely that there's this joint support mechanism. This would mean protection from depolarization. And what's less intuitive, and so I'll just assure you and maybe say a few words about it, but the dephasing mechanism that I should be worried about in the circuit is flux noise, because the 0 pi qubit has a superconducting loop. And so if the magnetic field changes, if the flux through that loop varies, then I should worry whether the qubit energy changes as a function of that. And it turns out that that part was already understood for fluxonium, that if you produce wave functions like this one or this one that sort of spread out over multiple local cosine wells, then a change in the potential due to a change in the external flux, actually, well, it'll modify the wave function. The wave function sort of follows this corrugation along as the flux changes, but the energy splitting is going to remain nearly the same. There's a fun PRL, I think maybe I'm listing it here. Yeah, there's a paper that is ancient by now that explains how and why that works. But it does. And so that's nice, because then if you can reach this parameter regime, you have indeed a circuit in front of you that has nice intrinsic protection from the most scary kinds of noise that typically limit superconducting, the coherence times in superconducting qubits. Let's see, it's 1:43. Well, at least here it is. I'll show you a little bit more about 0pi, but I do want to get to talk about this scqubits package. I know that one person actually contacted me that they use this package, and again, I'm very sort of proud of it, and we'll tell you a little bit about it. But so just to sort of finish up with 0pi, you can now compute eigenstates and eigenenergies. Since this is a multidimensional object, you can even, if you will, kind of draw little orbitals that signify along the three axes, where's just like orbitals in an atom, where's the wave function concentrated. And of course, we had to make predictions about coherence times. So when we did this work, there were no experiments yet. So we were interested in actually estimating what coherence times we could expect for certain parameters. And there's a whole zoo of things that you then have to try and compute and quantify. Not all of it is super reliable, in the sense that I would claim that it's still very hard to predict coherence times in an absolute manner. I think what we do know how to predict are trends. So if you tell me for a certain working point your circuit has this T1 and this T5, I can predict trends as you change your device parameters. And so you should take some of these numbers with a grain of salt, but they're interesting, because if you look at the order of magnitude, they're quite impressive, given what superconducting qubits usually do. So if you go into what we call the deep 0pi regime, then you can find T5 pure dephasing times and depolarization times that are way larger than anything that our current superconducting qubits can do. And I mentioned that there's sort of a depressing, maybe not depressing, but the current state of the art is it is hard to reach this parameter regime. And Brooks, Gitaev, and Preskel in their original proposal were actually aware of that. And they're theorists. They can do anything in theory, but they have this fun remark in their paper, perhaps you know it. It says, whatever method is used, reaching, say, a squared L over C of order 100 may be quite challenging. But in this paper, we take it for granted that this can be realized. That's sort of the luxury of being a theorist. You just say that, well, this may be difficult, but it's the experimentalist's problem. Well, it is the experimentalist problem, especially if you try. So Andrew Haupt's group at Princeton worked on this for a good while. Well, they reached a point in parameter space where the T1 was actually quite respectable, right? This is milliseconds. That's not something that you typically get for transmon. But the T2, even with echo, was below 30 microseconds, and that's maybe not so impressive. But in my mind, even historically, if you look at the performance of the first transmons were not that great either. And then they were optimized for multiple decades, and now they work quite well. And so that, at least from this historical perspective, I'm still excited about devices like 0pi, also Fluxonium, which is a little bit simpler, where I think there's still room for optimization, for improvement, and the chance that these devices might ultimately perform better than transmons. Okay, I do have one representation of a heavy fluxonium, which, everybody does something or did something during COVID, and I taught myself how to use Blender. So this was I actually have this as a poster above my desk now. This shows a fluxonium device as it was fabricated in Dave Schuster's lab, back then University of Chicago. And so the fluxonium, again, actually has these two big pads similar to a transmon. But then if you were to zoom in here, you would see that there's a big Josephson junction array, which turns this into a fluxonium rather than a transmon. Okay, and there's interesting work with multiple fluxoniums and two fluxonium gates going on. And I will skip over that in the interest of time and tell you a bit about superconducting qubits as they are modeled in this scqubits library. It's open source. We released the first version at the end of 2019, I believe. And by now it's acquired more than 100,000 downloads on Anaconda, on the Conda package manager. Don't confuse that with the number of users, which is going to be a small fraction of that, because every user might download multiple versions as they get released. But we've gotten nice feedback and worked with a number of people who seem to like this package and help us sort of improve it over time. And we think of it as something that has a twofold purpose. Number one, you can use it in the classroom, or certain parts of scqubits are indeed tailored to be simple and visual, so that this may make sense depending on the kind of quantum information class that you teach. But then it's also strong and powerful enough to actually serve as a tool in research. Research, there are a number of common tasks that repeat even before scqubits, obviously. You had to compute energy spectra. You would want to visualize wave functions, calculate matrix elements, then estimate coherence times, and then probably couple multiple qubits, couple them to bosonic modes, and then sort of explore these systems by performing parameter sweeps. Soon as you want to learn about dynamics of the system, probably you would want to interface your own code with QTIP. Those are maybe the important points that I want to make. And a lot of that is part of scqubits. So here's an overview. Maybe what I'll do is I'll just quickly jump over into a Jupyter notebook. But before I do so, I'll ask Justin at what time specifically I must stop.
I think there's some flex here, so if you need to go over a little bit, I think that's fine.
I don't want to go over, but if the tradition is that I should stop right here, then I will do so.
I think seeing a bit of demo would be good. So maybe aim for 5-10 minutes after, and then that leaves some time for questions.
Okay, sure. Thank you. All right, then I will jump over it there. Let's see. No, I will go here. All right, so now I'm in a Jupyter notebook. One thing that we will immediately experience is that my computer is relatively slow when Zoom is running, but it should be bearable. So I've already imported the package under the abbreviation SCQ. And then the simplest thing that you can do, which is actually quite nice, is you can say, I want to see the graphical user interface. If you've played with this before, I think what you'll get on my screen is a little bit different, because I've been trying to revamp that user interface just visually slightly, but all the functionality that you might know about is still there in the same way. So what do we see?
Sorry,
was there a question?
Professor, can you zoom a little bit so that?
Zoom?
Yes.
Like so?
Yes, that's better. Thank you.
Okay.
Thank you.
That means that I'll have to scroll back and forth, but I understand the issue. I see. So this is a graphical user interface that allows you to play with a number of superconducting qubits that we know and like. You can choose between transmons, fixed frequency ones, tunable, flux-tunable transmons, fluxonium, and more exotic things. If you are new to this and actually some of these names don't mean much, there's a simple way to get some basic information, usually coupled with some paper that you can also look up. And you can then, well, let's get rid of the qubit info again. You can look at the energy spectrum. This one looks particularly boring, which is actually a feature here rather than you know, this is in fact why the transmon is so charge insensitive. This is the offset charge that sort of represents this charge noise. Charge noise would wiggle on the x-axis, and you see energy levels are flat, and that's actually good for us. Let's maybe look at something a little bit more exciting. Let's go over to fluxonium. So now it's calculating, and it switches over. Wow, Zoom makes my computer slow. There we go. Here's the energy spectrum. And I apologize, but due to the Zoom, I do have to scroll back and forth now. And so you see, I can scan over flux. In principle, I can scan over other quantities that are actually not easy to change in situ, but they're fabrication parameters like EJ, EC, and EL. You can explore what the wave functions of your circuits look like. So here's the parabolic potential with the cosine overlaid. You see the wave functions. I could scroll back up somewhere, and I should be able to change the flux, which right now is hiding over here. So I can change that. It'll recalculate, and you see it shifts or it sort of modulates the potential a little bit. Wave functions look different. And so there's a lot that you can explore in terms of single qubits. You can look at matrix elements, which are important, of course, for can you drive the system, but also how sensitive is it to the environment, if the environment couples in a certain way. You can also look at estimates of coherence times. Those tend to take longer to compute. Without Zoom, just a couple of seconds. Probably with Zoom, we'll be staring at this for a little bit longer, but you can kind of get a feel for how does a circuit perform, what are its basic properties, just by sort of loading this graphical user interface and clicking on things. So even if you're not a Python expert and you're just interested in exploring a little bit, then you get to do this with this part of the package. And now you see here the estimates of coherence times, or at least contributions to the coherence times along different channels. So this one here is the dephasing due to flux noise, for instance. Here is sort of the typical dielectric loss and things like that. Okay, so I'll jump back into my presentation. And then it switches it around again. Now, I do not want to go a lot over time. This was the video in case my notebook had completely failed. I'll make a few final remarks about kind of the more powerful aspects of scqubits that we like to use in our research. So first of all, a single qubit is not enough. No quantum computer would be complete without having many qubits, probably coupled to each other, to resonators in between. And so there are simple ways in this package in which we can build up composite Hilbert spaces. I think I had a lot of explanation here how this works. You see there's more graphical user interface stuff that helps us to build up Hilbert spaces of multiple systems. And then I'll just jump to one example here where you see we can actually create transition energy plots similar to what you might see experimentally in two-tone spectroscopy. So this is the example of two transmons. They're actually flux tunable in this case with slightly different loop sizes, so that you see there are two different periods. They're coupled to a resonator, so you see the single 2-photon and 3-photon energies up there. And interestingly, this is functionality that is now used inside IBM Qiskit Metal. They like the functionality of performing parameter sweeps for composite Hilbert spaces that way. And so we talk a lot about some of the people also doing more app development right now as we speak that goes beyond Qiskit Metal. And the most recent thing that to describe in full beauty might take me too long a time, but I'll mention that for those of you interested in not just working with qubits that already exist, that are hard-coded into scqubits, you can make up your own circuit. There are limitations. Large circuits might just be too large and not fit into your computer's memory, but you can cook up new circuits, and as long as your computer is willing and strong enough, you can find energy spectra and such by this new circuit module that basically does circuit quantization for you. So it goes through an analysis of what kinds of degrees of freedom are present in the circuit. Along the way, you saw that there's some that look like fluxonium, which means that it's a variable that has a confining potential. In other cases, the potential may be purely periodic, which influences the boundary conditions. And then there's more pathological stuff that we also take care of. And then the package really goes through this whole set of steps to go from a circuit that you provide sort of as described as a graph, and it finds the Lagrangian, it sorts through the degrees of freedom and classifies them, it does some other useful things, and then via Legendre transform finds a symbolic Hamiltonian to you that then with some appropriate basis gets converted into the quantum mechanical Hamiltonian that can then be diagonalized. And so this is the newest part of the package that we also use in our research, and that IBM is also interested in for this for some of the new apps that they are currently developing. So there's in principle a lot that I could say about this, and I already anticipated to some degree that I might not get there, but that's all right. There are some things in this that where we try to be smart. So we, instead of diagonalizing the whole circuit by itself immediately, we kind of separate this into subsystems so that this huge matrix, which otherwise the Hamiltonian would be 25 million by 25 million, we do multiple diagonalizations and sort of scale this down so that we arrive at something that is feasible. But those are details that are probably only important to you if you use that particular part of the package. So I'll end with flashing this overview once more that shows you what are all the things that are currently part of scqubits, a whole bunch of different qubits. If you're interested in them, you can look at spectral properties, build up composite Hilbert spaces, do parameter sweeps. And we're currently working on a number of things. My former postdoc, Peter Gorskowski, is working on, there's already multiprocessing in this, so you can use multiple cores for parameter sweeps, but he's adding GPU support. We would like to improve the way that scqubits interfaces with QTIP, and there's some other things to do with noise that we're also working on. So I'll stop here. Here, the people that specifically contribute to scqubits is actually a large number of undergraduates who have been involved in that, because the Air Force gave us money specifically for undergraduate research on scqubits, and that has been a lot of fun. So this is where I should end. Thank you for your attention, and I'll be happy to answer questions.
Wonderful. Let's thank Jens, first of all, for a masterful talk. Very exceptionally clear, I would say. Are there any questions for Jens?
So
when you're talking about the 0 pi qubit, you talked about these 2 dimensions, but you mentioned that there's a third dimension or like a third degree of freedom. Could you talk a little bit about what that does? I think it's scattered on some of your slides, but could you explicitly?
Oh, I didn't understand the last.
It's sort of scattered on some of your slides. I think there's this zeta kind of thing. Could you mention more about that?
Yeah. Let me try and quickly return to. Can I do this? Does that work? Yes. Let's go. Let's go here. So 0 pi qubit is a circuit with 4 nodes. If I get my strange laser pointer to, where is my cursor? I can't see my own mouse cursor. So you see the circuit sort of centered on the screen. It has 4 nodes, which means that once you set one node to ground, which you're generally free to do, there should be 3 degrees of freedom. And they're sort of represented on the right. So if you were to linearize and replace your 2 Josephson junctions by yet another pair of inductances, then there are 3 normal modes. They correspond to this amplitude pattern of pluses and minuses as shown in blue. And the 2 degrees of freedom that sort of collaborate and form the actual 0 pi qubit that we know and like, that's the phi and theta degrees of freedom. They really couple together. So they're once you take into account that the junctions are junctions and not inductances, they go together, they couple. But then there's this other degree of freedom, which we call zeta here. And if you look at the pluses and minuses, again representing the signs of amplitudes of your normal modes, you see that there's actually no amplitude differences across Josephson junctions, which means that this degree of freedom is purely harmonic. This is just a harmonic oscillator. And what's not so easy to see from just waving my hands, but what I can assure you is that as long as you have this ideal case of the 2 inductances in the circuit are identical, the 2 capacitances are identical, the 2 Josephson junctions are identical, this harmonic mode completely decouples from the rest. It just doesn't want to talk to the rest, and it's only disorder in the circuit elements that makes it talk weakly. And it's a degree of freedom that Brooks, Kitaev, and Preskill, well, I don't know, overlooked or chose not to talk about in their paper. But it's there, and for a while it worried us for a number of reasons. But yes, there is this harmonic mode, and especially when you think about the coherence properties in kind of the deep 0 pi regime where you expect or hope for protection, analyzing its influence is actually quite critical.
Thank you.
Just following up on that, would it be fair to say that part of the difficulty in experimentally realizing this is getting all of those identical parameters to actually decouple that mode?
There's, I think the bigger challenges are, so I would agree that eventually what you mentioned becomes a challenge. However, we're not even quite there yet. So for this for us to reach this parameter regime, there's sort of requirements on how large must those 2 capacitances be, and how large must the 2 inductances be, and the answer is actually quite large. So for that reason, the inductances are made up of Josephson junction arrays. I didn't dwell on this, but that's a nice way to go, except that if you make this array longer and longer, and you think that, well, that's going to help, right? It's more and more inductance. You have to start worrying about spurious capacitance of all those metallic islands, well, to each other and to ground. And then, well, making these big capacitances as big as we want them, maybe that'll ultimately require to actually kind of go into the third dimension and have overlap capacitors rather than the big pads that are currently in use. There's actually not pads. I did have the device image, right? I just didn't explain it much at all. Here it is. So the two big capacitances are actually these two guys, where you have all these interdigitated fingers that try to make the geometric capacitance large. But even there, you see there's always this effect that, well, this piece of metal also has some good capacitance over to the ground plane, which is not what you want. And so some of this is the current challenge that you would have to overcome first before having to worry about how different are your elements and what would that mean for the coupling of this data mode.
Makes sense. Thank you. Are there other questions in the Dean's conference room there? No? How about other questions here on Zoom? No? All right, then I'll finish up with one question from me, just because I'm curious. I know you've done a decent amount of work with this, these gauge choices and setting up these Lagrangians, Hamiltonians, and so forth for circuit quantization. Has that shown up at all in your scqubit auto implementation of these things?
Let's see whether I understand which gauge choices you are referring to. Are you referring to how external magnetic flux is included in the quantization?
Example. Yeah, for example.
Yeah, so that's a really good question. When we started out this package, we actually didn't understand ourselves certain details yet. So as long as the magnetic flux that you have in mind is constant, doesn't change as a function of time, it's actually hard to do anything wrong, because you can, by simple variable shifts, you can shift, in fact, the term, the magnetic flux itself from one term in the circuit to another. And all of those options, as long as you don't make a mistake, are equivalent. They give rise to the same energy spectrum and such. But experimentalists like to change those fluxes as a function of time. And in fact, the flux has to get there somehow. So there's going to be some time dependence, even if it's in the past. And then indeed, there's a question of what do you have to do? How do you do it correctly? Well, if you ask me now, is the flux sitting in all the right places currently in the package? I am not going to bet my salary on it. I think our attempts with this circuit module have been to do that correctly. Overall, there's sort of a question of, what do we currently consider as the scope of the package? And I mentioned that one thing that we're working on is this interface to QTIP, which kind of signals that our package does not itself try to do dynamics, right? We think that QTIP is awesome for that. And we try to kind of get from the static side, which is scqubits, to QTIP. Yeah, whether, in Fluxonium, whether we currently put the external flux into the inductor term or the Josephson junction term, I would have to look up. Yeah.
Interesting. I was just curious because we're doing a lot with things like flux pumping, and I think that's exactly the case when this becomes important.
Yes.
So
that is absolutely right.
Maybe I can interject here a little bit, considering I've worked on this. Currently, in the state of scqubits as it is, you're using this expression for the Hamiltonian that's from the paper that you did on the dispersive limit of Fluxonium. Mm-hmm. So it's this already diagonalized form. Justin, so sort of, I was working on that Sorry, what was your question again, Justin?
Well, since this is starting to get into the weeds here, why don't we formally finish up the recorded segment of the talk?
Yeah,
And we can keep discussing afterward. So why don't we all thank Jens here again for a wonderful talk. And I'll let Sarah close up the recording.